modeling of electrical and mechanical systems, which is second part of unit first. So we model the transfer function with the help of model the electrical or mechanical systems with the help of transfer function, including passive network and operational amplifiers. So the principle which we use to derive the transfer function are Kirchhoff's laws, and we sum voltages around the loops and currents at the nodes and equate the result to 0. So this table summarizes the relationship between voltage and current and between voltage and charge for the three passive linear components, that is resistor, capacitor and inductor, provided that the initial conditions are 0. Okay, so you can write this table on your notebook. Copy this table. So from these relationships, we can write the differential equation for the network using Kirchhoff's laws. So then we can take the Laplace transform and solve for the transfer function. So if you take a capacitor, we know that the capacitor is represented by this symbol, and the voltage across the capacitor is given by the differential equation Vt equal to 1 by C integral 0 to t I tau d tau. So if we write in terms of current through the capacitor, It, from if you differentiate this equation, you will get It equal to C dVt by dt. Okay, and since Vt can be written as Qt upon C, right? Voltage is equal to charge upon capacitance. So if we take the Laplace transform, so it becomes 1 by Cs, and if we take the inverse of it, so it is Cs. Similarly, resistor is described by the ohmic transfer function Vt equal to Rit, and It becomes 1 by R Vt. So Vt is R dQt by dt in terms of charge, and the resistor, the coefficient of proportionality constant is R, and 1 by R is represented as G, which is called the conductance. So capacitor inductor is represented like this. Vt is given by L di by dt. It is 1 by L integral 0 to t v tau d tau, and Vt in terms of charge is given as L d2 qt upon dt2. And the constant of proportionality is Ls, and 1 by Ls is the inverse. So Vt is voltage in volts, It is current in amps, Q is the charge in coulombs, C is the capacitance in farads, R is the resistance in ohms, G is conductance in mohs, and L is H in henries. All this you already know, so you can write down the table. So the technique for simplifying the solution for the transfer function, we take the Laplace transform for the relationship between voltage and current across the capacitor, resistor and inductor to yield for the capacitor Vs will be 1 by Cs Is. If we take the Laplace transform of this equation, Laplace transform of Vt equal to 1 by C integral It dt. So if you take the Laplace transform, Vs becomes 1 by Cs Is, because integral is 1 by S. Laplace transform of integral is 1 by S. For resistor, Vs is Ris. Is is nothing but current in terms of S. Instead of T, we are using S, which is the Laplace operator. For inductor, Vs is Lsis, because L di by dt, so differential is represented by S. So Lsis. If you define the transfer function Vs by Is as Zs, which is similar to the definition of resistance, right, from here. So that is the ratio of voltage to current. Unlike the resistance, this function is applicable to capacitor and inductor and carries information on the dynamic behavior of the component, since it represents an equivalent differential equation. We call this particular transfer function as the impedance. Subsequently, the concept of impedance can be used to simplify the solution for the transfer function when Kirchhoff's voltage law is used. You can write down these three equations. Vs for in terms of capacitor, inductor and resistor, and the transfer function Vs upon Is is equal to Zs. Zs is the impedance. So please keep taking notes. So if you represent voltage and current sources, so energy sources are twofold. Voltage source represents the constant voltage to any load. Variation in the load do not appreciably changes the voltage. This is the symbol for voltage source, right? Current source delivers a constant current to any load. Variation in the load do not appreciably change the current. This is the symbol for the current source. Practically, a current source can be constructed from a voltage source by placing a large resistance in series with the voltage source. Okay, and for the circuit analysis convenience, we can recall the theorem which is called the Norton's theorem, and its dual is called the Thevenin's theorem. A voltage source Vs in series with an impedance Zs can be replaced by a current source Is equal to Vs upon Zs equal to Ys Vs in parallel with the admittance Ys. Right? So you can write down these two symbols and this voltage and current source definitions. So we can solve some simple circuits via mesh analysis. Transfer functions can be obtained using Kirchhoff's voltage laws, in which the voltage are summed around loops or meshes. We call this method as mesh analysis. So let us take an example, simple example of a series RLC circuit. So you have to find the transfer function relating the capacitive voltage VCS to the input voltage Vs. So this is the input voltage, this is the capacitor voltage. So you have to find out the relationship between VCS to Vs. Okay, so try to solve this problem in your notebook. So what you do, you take the summation of the voltage around the loop. So you apply the KVL, assuming initial zero conditions, and you can write the differential equations, integral differential equation for the network. Starting from Vt, you start with Vt and write the, you assume that the current is moving, flowing in this direction. So first component encountered is L. So current voltage across L is given by this equation, L di by dt. Then second is R, so RIT. Third is C, so 1 by C integral 0 to t I tau d tau equal to Vt. Okay, now if you want to relate between VCT and Vt. So what you do, changing variables from current to charge using IT equal to dqt by dt, you can write down this equation in terms of charge. So L d2 qt upon dt2 plus R dqt by dt plus 1 by C qt, because IT is basically dqt by dt, right? Rate of flow of charge is the current. So dq by dt is IT. So replace I by dq by dt. Wherever you have I, replace it by dq by dt, and you can write down this voltage in terms of charge. Okay, so you can solve, you can note down this problem. And you can further solve this problem to find the transfer function in terms of Vs upon Vct. Okay, try to solve this problem yourself. So if you solve, keep solving this, replace qt by c dvct by dt. So you can replace qt by c vct in this, in the previous equation here, right? Because you know that v is equal to q by c. So q is equal to cv. So you can write down LC d2 VCT by dt2 plus RC dVC2 by dt plus Vc equal to Vt. So now you can take the Laplace transform assuming zero initial conditions and rearranging terms and simplifying yields this. So you can write down VCS upon Vs like this. And you can represent this whole in terms of a block diagram like this. Okay, so please note down this problem, this solution, and we will continue with other problems. So let us move on. So the Laplace transform of the loop differential equation, assuming zero initial condition, is given by this: Ls plus R plus 1 by Cs Is equal to Vs, which is of the form that sum of impedances into Is equal to sum of applied voltages, right? So the last form suggests the circuit is shown like this, right? Ls R 1 by Cs Vs, and the voltage across the capacitor is Vcs, okay, in which we add impedances in series, we add resistors in series. So we notice that the circuit above could have been obtained immediately from the original network circuit, simplifying simply by replacing each component with its impedance. Okay, so we call this circuit as the transformed circuit, right? So in terms of, in place of L, we write Ls. In place of C, we write 1 by Cs. Okay, so this is how we transform our circuit from time to frequency domain. Conversely, we can represent is, we can transform it like this, and for which we simply apply the Kirchhoff's voltage law. So Ls plus R upon R plus 1 by Cs into Is equal to Vs, and solving for Is upon Vs. If we write for and reverse of the inverse converse of the transfer function, so if we want to show Is as a ratio of Vs, Is upon Vs, so that will become like this, right? And the transfer function will be written in terms of Is upon Vs, so it will become 1 upon Ls plus R plus 1 by Cs. But the voltage across the capacitor Vs is Is upon Cs, eventually leads to the same transfer function. If we want to find the ratio between Vcs upon Vs, so we get the same transfer function. So conclusion is that with the impedance concept, we can bypass the differential equation and directly use a transformed circuit to find the transfer function, right? So you can draw this diagram and write the differential equation, write the Laplace equations. Okay. So other steps to solve the complex electrical network with multiple loops using mesh analysis, we can take the following steps. Number one, replace passive element values with their impedances as we have done in the previous problem. Then replace all sources and time variables with their Laplace transform. So Vt will be replaced by Vs, It will be replaced by Is. Assume a transform current and a current direction in each mesh, right? Then write Kirchhoff's voltage laws around each mesh. Then solve the simultaneous equation for the output and form the transfer function. Okay, so let us take a numerical problem. Suppose this is the circuit. Okay. So given the network of the figure at the top and below, find the transfer function I to S upon Vs. Please try to solve this problem, and I have given you the solution also. So this is the original circuit having R1L, R2C. So what the step number 1 is, replace each passive element by its impedance. Okay, so replacing passive element by its impedance, R1 remains same, L becomes Ls, R2 becomes R2, and C becomes 1 by Cs. Okay, and then assuming a direction of the current flow. So since we are having two loops, so we have to assume two current flows. So I1t and I2t, and replace V by Vs, I by Is. So V by Vs, I1T by I1S, I2T by I2S, and VCT by VCS. Okay. So if you solve this using the previous, all the steps given in the previous slide, you will get this result. So I would like all of you to solve this problem yourself and reach to this conclusion. Let us continue further. So you can solve this by transformed circuit, and then you have to write the equations which can be found by summing voltages around mesh 1 and mesh 2. Around mesh 1, the KVL gives you this equation. Around mesh 2, KVL gives you this equation. Then you can combine these two by simultaneous equations in I1 and I2S. You can transform this like this and replace I1 in terms of, write them in terms of I1 and I2. Okay, it's not very difficult. So for the first loop, if you write down, so Vs is equal to R into I1, Ls, the voltage across, the current across Ls is I1 minus I2, because I1 is flowing in this direction, I2 is flowing in the reverse direction. So it is I1 minus I2, and that is equal to Vs. Similarly, in second loop, the voltage across Ls is Ls into I2 minus I1, then R2 I2, then 1 by Cs I2. That is equal to 0 because there is no voltage source in this loop, right? So that is what we have written here. So R1 I1S plus Sn Ls I1 minus I2, and Ls I2 minus I1 plus R2 I2 plus 1 by Cs I2 equal to 0. So you sum up I1 and I2 like this in these two equations, and then you can find out I2S by using this method, Cramer's rule. So you can solve it yourself and you can get this result, right? So you can take the notes. In terms of matrix notation, you can write down like this. I2S is R1 plus LS Vs minus LS0 upon determinant. So determinant is R1 plus LS minus LS minus LS, LS plus R2 plus 1 by Cs. The transformation of linear equations into matrix, you can write this. So the matrix form has Ax plus B. Ax equal to B, which is X is given by A inverse of B. So you can take the inverse of A, right? So Cramer's rule, you know how to solve the matrix using Cramer's rule. So from this, you get this I2S upon Vs. I2S upon Vs becomes Ls upon determinant of this. This determinant you can find out by multiplying these two elements minus this. Okay. So this actually you can write down the last equation in I1 and I2 takes the following general form. So sum of impedances around mesh 1 into I1 minus sum of impedances common to two meshes into I2 equal to sum of applied voltages across around mesh 1 minus sum of impedances common to the two meshes into I1 plus sum of impedances around mesh 2 into I2 equal to sum of applied voltage around mesh 2. Okay, so this is the generalized form of KVL written like this. So similarly, we can solve the circuit using nodal analysis. Transfer functions can be obtained using Kirchhoff's current law, in which currents are summed at the nodes. So we call this method as the nodal analysis. Let us take a similar previous problem of RLC network and using nodal analysis without writing the differential equation. So you can transform the circuit in the impedance form. So Ls R 1 by Cs, and you can directly write Vs in terms of Is. Okay. So we assume currents leaving the node are positive and currents entering the nodes are negative. Okay. So the incoming current is the current flowing through the series resistor and inductor, and the outgoing current is the current through the capacitor. Okay. So Kirchhoff's current law applied at the node gives this. So VCS upon 1 by Cs plus VCS minus, suppose we are taking this node. Current in this direction is positive, current in this direction is, there are two currents. One current is flowing across the capacitor, the other current is flowing in this branch. Okay, so current across the capacitor is given by VCS upon 1 by Cs, and the current in this branch is given by VCS, voltage at this point and the voltage at this point, and the negative of the two. So VCS minus Vs upon R plus Ls equal to 0. So this is KCL at this node. Okay, so you can find the transfer function VCS upon Vs from this equation. Okay, so if you do that, you get this 1 upon R plus Ls plus Cs into VCS is equal to 1 upon R plus Ls into Vs. So which is takes the general form of sum of admittances connected to the node into Vs equal to sum of applied currents at that node. Okay, so this suggests the following transformed circuit given now with current source and admittances rather than voltage and impedances. So if we are using the nodal analysis, we replace the voltage source by the current source. So okay, so you write 1 upon R plus Ls into Vs. Okay, this current source, right, into the impedance, the admittance, 1 upon Zs. So Zs is R plus Ls, so 1 upon R plus Ls is the admittance, and the admittance across the capacitor is 1 upon Cs, 1 upon 1 upon Cs is Cs. Okay, so this is how we form the transformation using nodal analysis. You can draw this diagram and write these equations, these three equations and this diagram. With the complex circuit analysis using nodal method. So these are the steps. Replace passive elements values with their admittances. Replace all sources and time variables with their Laplace transforms. Replace transformed voltage sources with transformed current sources. Then write Kirchhoff's current law at each node. Then solve the simultaneous equations for the output and form the transfer function. So let us do a numerical problem. Suppose this is the given circuit R1 LR2C network. Find out the transfer function I to S upon Vs using nodal analysis. Okay. So you write G1 as 1 by R1, G2 as 1 by R2. By replacing all the passive elements with their admittances and voltage sources in the series with an impedance to current source in parallel with the admittance using Norton's theorem. Okay, so replace this with Vs into G and R by G1. So the G1 is 1 by R1 and G2 is 1 by R2. We identify two independent nodes with the voltage as the inductor voltage VL. At this node, voltage is VLS, and at this node, voltage is VCS. So now we apply the Kirchhoff's current law at the two nodes, giving the concept of admittance. So admittance of the inductor is 1 by Ls, and admittance of capacitor is Cs. So write down KCL at this node and KCL at this node. So you will get two equations. So try to solve this problem. Note down this, draw this diagram and try to solve it. Meanwhile, I'll take your attendance, right?
Hello, ma'am.
Yes, question?
मैम ये ट्रांसफर फंक्शन ये वाले प्रीवियस स्लाइड में मुझे एक बात समझना है। ये
हम्म
ट्रांसफर फंक्शन आप
हम्म
लिख रहे थे I2/Vs,
हम्म
तो फिर ये अलग अलग भी हो सकते हैं क्या ट्रांसफर फंक्शन?
वो आपको दिया होगा प्रॉब्लम में कि आपको I1 अपॉन वीएस लिखना है या I2, वो गिवन होगा प्रॉब्लम में। कभी कभी होता है कि आपको I1 अपॉन वीएस निकालना है, कभी होता है I2 अपॉन या VCS अपॉन वीएस, जो भी आपको जिसका भी रेशियो निकालना होगा दैट विल बी गिवन इन योर प्रॉब्लम। उसके हिसाब से फिर आपको अपनी प्रॉब्लम सॉल्व करनी होगी, राइट?
अच्छा,
या अभी जैसे आपको VCS अपॉन VS निकालना है, तो दैट वे यू हैव सॉल्व द प्रॉब्लम ना। आपको रिप्लेस करना है, दूसरे सारे जो फंक्शंस हैं उनको एलिमिनेट करना है, सिर्फ आपके दो टर्म रह जाएं, VCS और VS रह जाएं। इस तरह से आपको डिफरेंशियल इक्वेशन सॉल्व करना है, राइट?
ओके मैम।
दैट इज
मैम एक सर्किट के एक ही ट्रांसफर फंक्शन होंगे या फिर अलग अलग भी हो सकते हैं?
नहीं, एक सर्किट का एक ही होगा, डिपेंडिंग अपॉन कि आपका ट्रांसफर फंक्शन में कौन से वेरिएबल्स आप ले रहे हो। अगर आप I2S अपॉन VCS ले रहे हो तो वो सेम रहेगा। आपका मेथड अलग हो सकता है, मैश एनालिसिस, नोडल एनालिसिस, कोई भी लगाइए, लेकिन वो दोनों का रेशियो सेम रहेगा। लेकिन अगर आप ट्रांसफर फंक्शन के वेरिएबल दूसरा ले लो, सेम सर्किट के कई ट्रांसफर फंक्शंस हो सकते हैं डिपेंडिंग अपॉन द वेरिएबल्स कंसिडर्ड इन द प्रॉब्लम, एंड दैट वेरिएबल विल बी गिवन टू यू इन द प्रॉब्लम। ओके,
हाँ,
या
समझ गया मैम।
very good question. This is how I want the class to proceed. This is a live class. Tell me your name, please.
मोहसिन।
Mohsen. Roll number
51।
51. All right. Very good, Mohsen. Tomorrow I'll be taking your class from 10 to 12. Huh? So I'll be taking two periods because you don't have any class from 10 to 11 and my class is from 11 to 12. So I'll be taking both the periods 10 to 12 because I need to cover the syllabus. I'm far behind. So I'll engage both the classes. Okay. So please come in the class by 10 a.m. tomorrow. All right.
Okay, ma'am.
Our next class is going on. Can we leave, ma'am?
Yes, you can leave.